Alright, now let's look at integrals and surface area. And you might think that this is exactly the same idea as integrals and solids of revolution for volume, but there are some slight differences. So we're only going to consider in this when functions are revolved around the x or y axes. You can easily extend these formulas to going around any horizontal and vertical line, and you could probably also, with some work, extend them to sloping lines. But for us, we're just going to consider revolving a function around x or y axis. And two formulas. So if I'm going around the x-axis, so revolved around the x-axis, the surface area is going to equal the integral from a to b of, actually I probably don't need that, 2 pi f of x times the square root of 1 plus f prime of x squared dx. And if I'm revolved around the y-axis, the surface area is going to be pretty much the same thing, except I'm going to have a function in terms of y and a dy here. So surface area equals integral from a to b of 2 pi g of y times the square root of 1 plus g prime of y squared dy. So next slide I'm going to outline a proof. I'm not going to go all the way into the nitty gritty, but I'm going to explain why these are the formulas, and then I'll go through two examples. The examples for something like the AP test, well, the surface area I don't believe is on the AP test, but without a calculator you can set this up, but it would be very difficult to solve, to evaluate one of these integrals unless f of x is a constant or a linear function, because of all these little bits and pieces here. So I'm going to set up the integral, but then I'll just go to the calculator to get a numerical solution. So before we do that though, let's see why we have what we have. And the reason is this. So we know that for the lateral area of a cylinder, it's going to be 2 pi times the radius times the height. And that might lead you to believe that, so we might think that that's going to cause the surface area to be some type of integral of 2 pi. The radius is going to be given by the function, and the height, infinitesimally small height, is going to be given by this differential. But there's a problem here. So this is not the whole formula. If I flip back, you can see there's more to it. There's something else hanging out here. And the reason for that is the following. This is the case if I were to, so let me draw some axes. If I were to consider a horizontal segment that's revolved around the x-axis, then I would be fine with this formula as is. But what happens is when the function is not horizontal, when it's sloping, I'll just make something that's sort of a truncated cone here. The area formula changes, and this is why. When I take a small piece of this, I get a rectangle whose base, so it's going to be a long, thin rectangle. The base is going to be 2 pi r. In this case, r is that y value, that f of x. And whose height is going to be this here, this change in x. But down here, if I take a slice, and it's a small enough slice, it will be almost rectangular. The top and bottom will be almost the same size. When I make it smaller and smaller, it approaches the same area because there's such a slight difference. So I'll consider it as a rectangle. But the big difference is the height of this rectangle isn't dx. It is the hypotenuse. It's the hypotenuse of this little triangle here, which can be a larger proportion different. So this is missing something. And what's missing is that hypotenuse. So instead of having that, I'll have surface area equals integral from a to b of, I have 2 pi f of x as sort of the base of my rectangle, 2 pi f of x, but the height of my rectangle is going to be that same thing we got from the previous lesson that we used for length of a curve, times the square root of 1 plus f prime of x squared dx. Because if I have a function, let's consider this as a function, and I'm making it linear because we're looking very close, so if it's differentiable, it'll be locally linear. If I make a right triangle and have this be 1, then this difference here will be f prime of x, and this length here, the hypotenuse, is going to equal the square root of 1 squared, which is 1, plus f prime of x squared. So that's why we have this extra term in here. The rest just comes from sort of a cylinder. Now, let's go ahead and try a couple of problems. Example 1, find the area of the surface formed when c of x equals the square root of 1 minus x squared from x equals negative 1 to 1 is revolved around the x-axis. First thing, I'm going to dive in and just do the calculus and algebra without thinking about what this really is. Then we'll come back and see why it all makes sense. So in order to have this, I have this surface area is going to equal the integral from a to b. I guess in this case I know it's going to, well, I'll write the whole formula. A to b of 2 pi times c of x times the square root of 1 plus c prime of x squared dx. What I need to find is c prime of x. Well, if c of x is the square root of 1 minus x squared, I'll need to use some chain rule to get that c prime of x is take care of the square root and get 1 over 2 root the same thing, 1 minus x squared, times the derivative of the inner function, which is going to be negative 2x. And that gives me the negative 2 over 2, the 2's cancel, so I get negative x divided by the square root of 1 minus x squared. And now I can just write out the formula, so the surface area for this problem will equal the integral from negative 1 to 1 of 2 pi times the square root of 1 minus x squared times the square root of 1 plus negative x divided by root 1 minus x squared squared dx. And let's go and do this in the calculator. So I have to type this in carefully. math 9 for the integral. The function is 2 pi times the square root, and I open one set of parentheses, 1 minus x squared, close off that parentheses, times another square root, 1 plus, and I'll open up another set of parentheses for this, negative x divided by, and I don't need parentheses here because when I put the square root in, I'll get a set of parentheses, 1 minus x squared, close off the parentheses for the square root, close off the parentheses for the fraction, square that, close off the parentheses for this square root, and now I've taken care of the function. The variable we're integrating over is x, we're doing dx, from negative 1 up to 1. Now this could take the calculator a little while, let's see what happens. Hopefully it's not too long. 12.566 approximately. Now, I said this wasn't going to be surprising. This was what we should expect because, recall, what we have here is a circle, or a half circle, with radius 1, revolved around the x-axis, which means I'm going to get a sphere with radius 1. Surface area for a sphere should equal 4 pi r squared, which is going to be 4 pi, because r is 1 in this example. And it looks right. Let's check to make sure. 4 pi is pretty darn close. Okay, one more example. This example, we won't end up having a nice geometry formula to go back and check our answer, but as long as we do everything carefully, we'll get the right answer either way. So in here, the biggest difference is I have a function in terms of y, so instead of having the stuff written dx, I'll write this surface area as the integral from a to b of 2 pi f of y times the square root of 1 plus f prime of y squared dy. Common mistakes, just like with length of a curve, is people will forget to take the derivative here. They'll just put the regular function in and just get a wrong answer, so be careful with that. We know that f prime of y is going to be equal to negative sine of y, because the derivative of cosine is negative sine. And so the surface area is going to be the integral from 0 to pi of 2 pi times cosine of y times the square root of 1. And I'll skip the step here. When I put in negative sine of y here and square it, I get plus sine squared y dy. And as long as I did this correctly, and as long as I type this in carefully, which I'm going to do now, I'll get the right answer. So math 9, type in the function, 2 pi times the cosine of, and I'll just use x's here instead of y, it doesn't really matter, but it's faster to use x's because I can just press this button, x times the square root of 1 plus, and I can put the sign in parentheses, I can do it like this, sine of x, close off both the parentheses and square it, not x it, square it. I could also, and this is the way I type it, just type it like this. The calculator will do sine squared x this way. Just be careful not to put the squared on the x. That is the sine of x squared, which is completely different. And I'll close off the parentheses for the square root, comma, x, comma, 0, comma, pi. And this gives me, hopefully not an error, let me see. So where did I mess up? Okay. So in here, what went wrong is this. So I can't possibly have this be 0. The problem is, and I'll show you here, the problem is this. And I'll fix it and get a better answer. So we're dealing with this function here, cosine of y. And when I revolve this around, I get this sort of hourglass shape, which is, nice to have. But here's where the problem comes in. The problem is when I'm going from 0 to pi over 2 in this sort of domain, because y is my input, the r is positive. When I'm going from pi over 2 to pi, the r is negative. So I have a few options here. One option, I could put absolute values here because I want to make sure that the radius is positive. And that's, I'm not going to do it that way, but that's one option. Another option is I could split it into two integrals, do the first integral from 0 to pi over 2, and then do the integral from pi over 2 to, or sorry, not from 0 to pi over 2, yes, sorry, I'm lying, from pi over 2 to pi of negative cosine, because in that interval cosine is negative, so negative cosine will be positive. So I haven't seen very many problems where that is an issue, but just to be clear, if the function does go negative, since unlike with solids of revolution, we're not squaring this term, I had to make sure that I keep things positive. So let me fix that in my calculator. So math 9. So I'll do the integral. Actually, let me do it this way. So second entry, and I'll go from 0 to pi over 2. $7.211799, and I could store this as a variable. I'll do that. Store this as a, and then I'll go and do the integral from pi over 2 up to pi. So I'll get the entry second one, and if you're careful and you notice, it's going to be the same thing. You can see it's symmetric, but I'll type it in just so that we see it does work out that way. So pi over 2 up to pi. And to take care of this, to make the radius positive, I'm going to put in a negative cosine. So second insert negative cosine. And lo and behold, we get the same thing. I'll store that as b. And now I just need to do a plus b. And we get 14.424 approximately. So let me fix that. Okay, sorry that I didn't put this in the beginning. I just didn't even realize it would be a problem because I've never seen problems show up before where they go negative, but clearly it is. It's an easy fix. If you have questions, feel free to comment below.